Okay, today I want to introduce the idea of a degree of a map. So if we're given some function, continuous of course, from Sn to Sn, then we know that this map induces a map on homology. In particular, I'll look at the nth homology group, because that's the only interesting one. All the other ones die, except for 0. But in reduced homology, all the other ones die. Here, the interesting one is n equals 0. And you know, both of these are secretly a copy of z. You know, this is a copy of z. This is a copy of z. So you should think that this map is just sending z to itself. OK, so what could it possibly be? It's a homomorphism that sends z to itself. So what does it look like?
Either identity or negation.
Those are two possibilities. Or times whatever, just a homomorphism, not an isomorphism, right? This map you can think of as just times d. It's the times d map, where the generator of this guy, 1, you just see where he gets sent, d, and that tells you where everything else gets sent as well, right? 2 gets sent to 2d, 3 to 3d, and so forth, because this is a homomorphism. So it's just times d. We're going to call d the degree of the map. So we call this d the degree of your map f. OK. There are a lot of properties we can immediately identify about degree. What is the degree? I'll often denote this. So I'll often denote the degree of f by just degree of f, which is just equal to that whatever the number d is. What is the degree, first property, of the identity map? Just 1. That's right, because the induced map here is itself just going to be the identity map, right? The induced map just comes out to be the identity map on Sn. Okay. Second property. Suppose f is homotopic to G. Then, what can you tell me about the degrees? What does that tell you about degrees? Well, we've already said if these guys are homotopic, then their induced maps are the same. So the induced maps are equal to each other. So then, of course, the degree of f will have to equal the degree of G. Okay. That direction is straightforward. It turns out the converse is also true. This converse is a theorem of Hopf. And it's proved in chapter 4 of Hatcher's book. We probably won't get there this semester. So this shouldn't be obvious why it's true. But this is kind of telling you that degree gives you a complete classification of maps between spheres up to homotopy, right? So degree is really the thing capturing what the map is up to homotopy. A few more properties. Probably fit them up here. What is the degree of f times g? Well, recall the induced map on f times g is just the induced map on f times the induced map on g. So that's just a composition of whatever the induced map on g is with the induced map on f. And so if g is multiplying by some d1 and f is multiplying by some d2, then the composition is multiplying by the product of those. So this will just be the degree of f times the degree of g. Good? Okay. Let's look at some particular functions. What is the, we're now space here, so I'll come over here. What is the degree of f where, let's say f is a particular function, let's say it's a reflection. Then you tell me what will be the degree of f. So I'm thinking here, I have something like maybe S1 or S2. Here's S1, and I'm just thinking that my f is a reflection. You can choose what you're reflecting over. Let's say here I'm reflecting over this horizontal line. So you can do either symmetry you want to, but we'll just reflect over the horizontal line. So that points up top are being mapped to the reflection on bottom. So this is f. What's going to be the degree of that guy? Well, you might immediately notice that f squared is just identity. Reflect twice, that's identity. So that means the degree of f times the degree of f should give you the degree of the density, which is 1. So that gives you that the degree of f is plus or minus 1. So just by using this property, we know the degree of a reflection is plus or minus 1. But if you actually want to know what that degree is, we got to think a little bit more about what actually is this map on homology. So I can think of my S1 here. I think of it as like being a CW complex. Then I have my top hemisphere, I'll call that like A, and my bottom hemisphere, I probably shouldn't have used green, B. Or more generally, if you're thinking in higher dimension, your S2 has some top hemisphere, maybe I'll call that like big A. That's this top bit. And B that's the bottom bit. And then there's your equator, which you can think of as however you want to, with points and edges between them. But if we go down and think on the level of homology, we can do either one you can think about. I'll do the case of S2, it's very similar with S1. What is H2 of the sphere? We've already said it's isomorphic to Z, but like, what is it generated by? What is it generated by? And here, well, it depends how we put our orientations nice. But if we orientate things the way we typically do, I think with this example, maybe like the first lecture or something, this is just A minus B. So then you think, if F's the reflection map, what does the induced map on reflection do, sending you here to H2 of S2? And you're like, well, A minus B will get sent. Let's think what reflection does. Reflection just sends A to B and B to A. So this will get sent to B minus A. And so the generator here, if you think of generator as being like 1, will get sent to -1 in the Z over here. So my degree of this map is equal to -1. So it could have been plus or minus 1, but it comes out to be -1. And you can think about this in other settings as well, like S1 or Sn in general. Okay, so that's the idea of the degree. If you have some map from Sn to Sn, you can look at the induced map on the nth homology group of the sphere, We know that's just a copy of Z, so it's a homomorphism from Z to Z, so it's just multiplication by some D. We call that D the degree of the map. The degree of identity map is 1. Degree of reflection is -1. Satisfies some properties like if two maps are homotopic, they have the same degree, and the composition of two maps has degree equal to the product of the degree of those two maps. We can do one more, and then we'll use this to prove a really nice theorem. Well, I don't know. Yeah, I think it's nice. What if F is the antipodal map? So often this is denoted minus identity, the antipodal map. So antipodal just means some point in your sphere, some point x is going to get sent to minus x. Well, this is on the, if this is on the front, this is on the back. Where so if you think of this as being embedded in n-dimensional space, in this case if it's embedded in R3, you would think of this as being some x1, x2, x3. Well, then this is going to get sent to just minus x1, minus x2, minus x3. If you think here of your S2 as living inside of R3. So you can give these coordinates. Can you tell me what is the degree of the antipodal map?
Depends on dimension, right?
Okay. Say more.
Well, like with like S1, that would be the antipodal would just be kind of like a rotation. So then it would be homotopics would just be 1. So if it's
So with S1, you want to think of the antipodal map which sends like some x here to its point -x. What if instead of thinking of it as rotations, another way you can think of it? I want to think of it
there's two reflections.
as a composition of reflections, that's right. So there's one reflection that takes me down here, and then there's another reflection that didn't draw it perfectly, takes me here. And if you just keep track of what's going on, if you think of this x as being x1, x2, so here I'm thinking of my S1 as living inside of R2, the first reflection is just inverting, I guess in this case it's the x2. So it's making one of these guys negative, the second coordinate negative. And then the second reflection is making the first coordinate negative. So each reflection makes one the coordinates negative, right? Okay, so if I'm doing this map on Sn, you can think this is just equal to the composition of how many reflections? Yeah, in S1 you need 2 reflections. In S2 you need 3 reflections, 1 for each coordinate. In Sn you need n plus 1 reflections. So this degree, by this property right here, would just come out to be -1 to the n plus 1. Good? Okay. So that's all we need. I mean, all we've done is we just use the fact that Hn of Sn is Z. And then think a little bit about this idea of degree. But that's the only tool we need to prove the Hairy Ball Theorem. Okay, you've probably heard of this one before, perhaps not. It simply states that if you're in a setting like S1, and you have little hairs on S1, what do I mean by hairs? I mean a vector field, a continuous field of my tangent vectors, then I can draw. Since a continuous vector field. So these are just all my tangent vectors, the non-zero vectors all the way around. So I have a continuous field of non-zero vectors. But in S2, you could try to come up with some continuous field of non-zero vectors. So maybe around the equator, we just play the same game we did in S1. So you would have these little tangents. And it's kind of hard to represent these on the back. Maybe we'll do something like that, dotted lines. Okay, so you can do that. And you can do that, going up all the way around. You can think they're like circles around the sky. Circles going up, circles going down. And on each one, you can draw a similar continuous field. But where does this go awry? As you approach the North Pole, like this would tend towards, well, there would be no value. You could put a zero vector, but there's no non-zero vector that you put there that wouldn't break continuity, right? So, and same thing as South Pole. At these poles, it wouldn't be continuous. And so one way you can kind of think of this with hair is if you have hair growing off of a circle, you can comb the hair around, right, in this nice continuous way. But on a ball, if you comb the hair around the ball, you get cowlicks at the top and the bottom, right? Like on the back of your, well, mine doesn't. And typically, your hair has a place where the hair parts, right? Meaning that there's no non-zero vector there. Okay, now it's hard to imagine this for S3 and S4 and so forth. But what turns out to happen is that Sn has a continuous, non-zero, tangent vector field. This n here is positive. If and only if n is odd. So this result that holds true for S1 and S2 generalizes that you can find it for odd SNs, but not for even SNs. I mean, it's not even obvious that you can't find it for S2, right? Like maybe this, you're like, well, maybe this is a really clever one, and you can try to think about what that clever one might be, but this says no matter how you try to comb S2, there will always be places where you break either continuity or you have to have a non-zero vector, right? Okay. So let's prove this. Let's suppose we have such a vector field. Where I'll call Vx the tangent vector associated with, so I'll make x little vector, at the vector x, which is some vector in Sn. So the picture I have in mind now, I guess I could draw it here, is if here is some vector x, which really means your vector is at the origin and it just points and it hits the sphere at this point. So if this is x, if that's what x from the origin comes up and hits on your sphere, then you have this Vx would be this little vector pointed this way. This would be your vector V of x. Right? Okay. Note, whenever this is true, whenever you have a tangent vector in a sphere, we know that your vector x and v of x are orthogonal, they're perpendicular to each other. Which is to say, if you take this Vx and draw it inside of the sphere, you know, okay, kind of having a tough time now. You can do this. So here was some vector, here is your x that takes you some point here. And you think at x, you think that at x, you have some little tangent vector. Non-zero tangent vector v of x. But if I scale this so it's unit length, that's going to come out to be some, looks like it's just going out like this, some little vector that hits over here somewhere, so that these are orthogonal to each other. So this would be this scale to a unit length. So that's your tangent vector Vx divided by the magnitude of Vx. Now it's length 1, so it lies on the sphere as well. So now you have x and Vx scale to unit length, both being points lying on the sphere. Okay, what we're going to do is we're going to consider a function from Sn to Sn. And what this function is going to do is it's just going to look at points that you can think of linear combinations of these two. So it's going to end up giving us something like a great circle of giving you points that depend on those 2 points. So I'll define it explicitly right now. F of a vector x will be equal to, oh, well, maybe I shouldn't use x. That may not be good. I'm fine using x. Because you have this, these are defined for every point x as well. At every point x, we're actually going to make f a family of functions over the parameter t, so that this is defined to be, get the order of these right, yeah, cosine of t times the vector x. This is some scalar times the vector x, plus sine of t times this unit vector. So it's the Vx scaled to be a unit vector. Okay, so what you should convince yourself of is that this is always of unit length. So it's like, what is the magnitude of this for any value t in any point x? Well, these are both unit vectors, and here you have the property that your coefficient here squared plus coefficient here squared, sine squared plus cosine squared is 1. So this comes out to be unit length. And so indeed, this is always spitting out some value on Sn. This is just spitting out the values. This is the parameterization of this circle. So what you're doing is just traveling along the circle. Well, I guess you're traveling from, well, let's see exactly where we're traveling. Like, let's pick some values of t. Like, let's let t be equal to 0. Then you tell me, so I mean, you write that, I can just call it f of 0. What is f0 of x? Well, your cosine is 1 at 0, and your sine is 0. So at time 0, you just start off at x. Now, by the time you get to pi over 2, this vanishes, and your sine is 1. So you start off at x at time, so you're here at time equals 0, and then at time pi over 2, you're down here, right? So you can think it's moving you, you're just moving along this arc. But then keep going. Don't stop at pi over 2. Let's go until we get to, say, time pi. At time pi, where do you end up at? Yeah, at time pi, cosine is just -1. This is 0 again. So you're at -x. So what we have here is a homotopy that starts off with the identity map and ends up with the antipodal map. So what we've just shown is that identity is homotopic to the antipodal map. But if two maps are homotopic, come back over here, we said if two maps are homotopic, they induce the same map on homology, and therefore they have the same degree. So that means the degree. So from this, we get that the degree of the identity map must secretly be the same thing as the degree of the antipodal map. But as we just said in the setup, the degree of the identity map is 1, and the degree of the antipodal map is -1 to the n plus 1. And the only time -1 to a power is 1 is when it's an even power. So n plus 1 is even. And if n plus 1 is even, that means n is odd. Okay. So that completes the proof. Well, okay. That completes this direction of the proof, and then you have to convince yourself in the other direction works as well. If n is odd, well, then you know these are equal, so then there exists such a homotopy. Okay, think through the other direction. But we've certainly proven this direction. Okay, good. That's the Hairy Ball theorem. That's our first application of degree. But it's not the main reason I'm showing you degree. The main reason I've shown you degree is because I want to introduce a new homology theory. That's going to be defined using degree. So up until this point in the course, we've seen two homology theories so far. There are two ways of defining homology. The first one was simplicial homology. So we had some H. What was our notation? How do we distinguish did we have any notation to distinguish? Did we do like a little delta complex here or something? I think that's what we did. So we had simplicial homology, and then we had singular homology. Singular homology. And I'm not going to hash through these definitions again. You can go through the previous lectures. But we defined these two homology theories. And then was the last class, we used the Phi lemma to sketch the proof that these are actually equivalent to each other. So different ways to define homology, but gives you the same theory. Today I'm going to give you a third homology theory, and which is secretly equivalent as well. But sometimes having several different ways of defining these homologies gives you different ways of calculating, and sometimes it's easier to calculate homology into one such account than another. So what we're going to do today is define cellular homology. And the way cellular homology is defined is going to be defined for a CW complex. So I should take a few minutes to remind you what the CW complex is. You can go back, I think it was the first lecture, it's lecture 0, where we introduced these, but maybe you forgot. So a CW complex is a space, a topological space, that we're going to build up one dimension at a time. And so you begin with the zero skeleton. So this is often denoted x0, it's the zero skeleton, which is just a point or possibly several points. It's your zero-dimensional stuff. Okay. I'll introduce the notation, the -1 skeleton, but that's just the empty set. But we'll want a convention to say you have nothing. So you begin with -1, you begin with nothing. Then you add zero-dimensional things, those are points. Then you have your 1 skeleton. And the way you get your 1 skeleton is by attaching 1 cells to the 0 skeleton. So what is a 1 cell? recall one cells are just open one-dimensional disk. So these are open, maybe I'll do like little open balls at the end. These are open one-dimensional disk, which is open intervals. And then what you do is you look at the boundary, where the boundary points would be, and you attach those, you attach the ends here to the zero skeleton. So you have some attaching map where this attaching map is here, these two endpoints, well, the two endpoints you think of as S0 is just a map that's telling you how to send S0 onto your zero skeleton, onto X0. And so if I just say, well, attach both of these here and attach both here, I would just end up, say, with two loops, with one loop, with two loops on here. That's your one skeleton. And then you can build up to a two skeleton. So how do you get a two skeleton? Well, now I want some two cells. So you want to attach a two cell. Well, you can think of a two cell as just being an open two-dimensional disk. Open two-dimensional ball. Okay. But think of it as being open. And then it's attached around what the boundary of the closure would be. So here, this attaching map, the boundary of this is S1, and that just gets attached onto your one skeleton. So it's a map from S1 onto X1. And how might you glue this disk on here? Well, you might have some instructions, like if this was called like A and B, where it's like glue along A and then glue along B and then glue along A backwards. So if these have orientations, you can keep track of some orientation on these guys. This was my A, this was my B. You have some orientation. Glue along A, glue along B, glue along A backwards, glue along B backwards. What does that give you? The torus. So then your two skeleton now looks like a torus, not filled in, not a solid torus, just an empty torus, where you can still think of, okay, I still have this structure from the previous points, but it's been filled in now with a two cell. And you keep building it up this way, okay? So in general, an n cell I'll denote as e to the n. If there's several of them, I might give them some subscripts, so I can have subscripts for them. So n cells, I might give them like e to the n1, e to the n2, and so forth. And you have an attaching map. Each one of these are just n-dimensional balls. And you have an attaching map where this each e to the n, the boundary of it, which is just an s to the n minus 1, gets attached onto your n minus 1 skeleton. And this is how you build your xn from the n minus 1 skeleton by just attaching some n cells to it. Does this sound familiar? Are we happy with this? Okay. I'm reviewing this all because we're going to find out cellular homology, which is just going to be defined in terms of some cellular structure. So whenever you have a CW complex, that means you have some way of building up your space by attaching cells. We'll be able to, from that CW complex, be able to read off the homology. So this is quite nice. It's kind of like simplicial homology, but you don't need to have a singular complex or a delta complex. You can just have your CW complex. So in that sense, more powerful. But we're going to see it comes out to be the same. Okay, so how do we define this thing? Well, with any homology theory, we always have some long exact sequence. We have a long exact sequence, And then we just define the homology as you have these maps between these abelian groups, and each map you define as the kernel of the one over the image of the previous, right? So I need to give you a long exact sequence. Okay, so here is the long exact sequence. It looks like this. This is the nth plus 1 homology group, relative homology, of the n plus 1 skeleton, rel the n skeleton, mapping to the nth homology of the n skeleton, rel the n minus 1 skeleton, mapping to the n minus 1 homology of the n minus 1 skeleton, rel the n skeleton, and so on. You're like, well, how does this thing end? Well, that's where once you get to the 0 skeleton, it's the 0 skeleton, rel, oh, sorry, this should be n minus 2. Rel the n minus 2. Once you get down to h0 for the 0 skeleton, it's rel the n minus 1, which would be the minus 1 skeleton, and that's why here I just define this to be the empty set. So like, if this thing keeps going, it'll go to h0 of x0, x minus 1, but I just had to find that to just be the empty set, which means it's just h0 of x0, because rel nothing, mapping then to 0. So that's how the log exact sequence ends, right? Okay. Then we have boundary maps, dn plus 1, dn, and so forth, where the composition of two boundary maps, where dn of dn plus 1 comes out to give you 0. Okay. I am not going to prove that this is a long exact sequence. This will follow very quickly once I define what this map is. So, you can look in Hatcher, nice proof. It's actually very clever proof. And okay, I can give you like the very quick idea of it. What you do is you say, I already know that this shows up in a long exact sequence. So like, maybe what I'll do, this is the crudest of sketches. It's like, I already know this shows up in a long exact sequence. Do you remember the long exact sequence that this guy shows up in? It's the long exact sequence we had for a pair, a good pair. This just comes out. So just think like this is x rel some a. There was a long exact sequence for that. What would be next in the long exact sequence? It would be hn of the a, xn, mapping to hn of xn plus 1, and so forth. So this itself is a long exact sequence we already know about. So we already have this long exact sequence. And then you say, these guys together feature also in a long exact sequence we already know about. Where here you would have had hn of x, so up here is like hn of xn minus 1, and that maps down here to hn of xn, and then you get xn rel xn minus 1, and then that maps down to hn minus 1 of xn minus 1. Okay, I was trying to avoid sketching this proof. But then what you'll do is do a little bit of diagram chasing to convince yourself, if I define this map just to be the composition of these two maps, right? So if this is some, I and j or whatever is a composition of those two maps. So this is actually how you can define this. Then what you can do is you can prove the exactness of this sequence. And this crisscross pattern continues. And so you can use the fact that we already know that these diagonal guys are long exact to prove that this is long. It's good activity to do. So you can either try to do this on your own or read through Hatcher's explanation of it. But it's just diagram chasing and thinking through that satisfies all the properties. I don't necessarily want to take a long time on it. Is that believable? Is that good? Okay. So this might look like a mess because it's a long exact sequence where your groups themselves are homology groups. I haven't even defined the homology yet. So this long exact sequence is called the cellular chain complex. Let me put that up here. This is called your cellular chain complex. Before we had chain complexes, this is my cellular chain complex. Cellular chain complex. But if I want to define cellular homology, my definition will be Hn of cellular homology. This is my notation for cellular homology. So this is cellular homology. Will be defined to be the kernel of Dn over the image of Dn plus 1. So your groups themselves are homology groups. But then you find your cellular homology on this. So these are relative homology groups, and on that you define homology. So this might seem like excessively messy, complicated, ugly. But these relative homology groups are very nice. What is Hn of xn rel xn minus 1? So you should think this is just like collapsing down everything in the n minus 1 skeleton, only leaving the stuff you added in the n skeleton. So what are you left with? Like, think back here. You know, if I collapse down everything, just leaving this like 2 cell, but I collapse all of this, what am I left with? Well, the boundary of this have been glued to this. So it's just like your 2 cell with the boundary collapsed down to a point. So what are you given? It's a sphere. So each 2 cell will contribute a sphere. And so this just comes out to be a wedge of spheres. So this is just Hn of a wedge of spheres where you have 1 sphere for each 2 cell. So here, I made it index I, but what I'm just trying to say is this is indexed over your 2 cells. You have 1 sphere for each 2 cell. Or in this case, n cell. N cell. Okay, so what do we come out with? What's the homology of that? Have we talked about this? Ooh, did we talk about the homology of a wedge product? I'm not sure if we did. That would have been a good exercise. Okay. It's the obvious thing. What is it? It's just the direct product of z's. So the homology of a wedge sum is just the direct sum of the homology of each of the summits. So it's just the direct sum of z over I. So you get 1 copy of z for each 2 cell. So if you prefer, it's like, it just comes out to be z, it's just z, not 2 cell, n cell, to the number of n cells. You know, this is the number of n cells. That's where you end up with. Okay? Okay. I still need to show you, talk about what this map dn comes out to be. And we'll do that in a second. Hint, it has to do with degree. That's where I spent so much time talking about degree. But I think as I talk about that, it would be good to set up a concrete example. So let's try to find the homology of a torus. The cellular homology of a torus. Now, I'm not going to have time today to even begin to sketch this. So I'm just going to do maybe 2 or 3 examples to round out our time today. But spoiler, just like before, your cellular homology will come out to be the same as your singular and simplicial homology. So I'm not going to have, we're not going to prove this, that's fine. What I want to do is actually show you, you refer to Hatcher, you can read the proof, it's very nice. But I want to just show you how to actually calculate using this homology theory. So for a torus, so what these maps become then are just copies of Z for your 0 cells, 1 cells, 2 cells, and so forth. So your exact sequence, you just think you have 0 cells, you're going to have 1 for 1 cells, you're going to have 1 for 2 cells, and so forth. Well, your torus, we just drew it over there. It doesn't have anything higher, so everything higher will be 0. How many 2 cells do you have? Just the 1, right? It's just a copy of Z. How many 1 cells were there? 2. So that's a Z squared. And then 0 here is, there was a single point Z. So remind you of the construction. You had a single 0 cell. You could call that X. Then we added in our 1 cells. One cell going this way, you can call that A. One cell this way, you can call that B. And then we glued in the 2 cell, creating a torus. Right, so that's my attempt at drawing a torus. Okay. So that comes from gluing in your 2 cell. Okay. What I need to tell you is what this map D is, so we can actually calculate homology. So here's the formal definition of Dn. Dn is a map from Hn of xn to xn minus 1 to Hn minus 1 of xn minus 1 to xn minus 2. But we are just thinking of both of these as being a wedge of spheres. One sphere for each n cell. So this you're thinking of secretly as being a wedge of n cells, of spheres that become SNs. And this you're thinking of as a wedge of n minus 1 spheres. So if I take a generator over here, a generator, one of these generators will correspond exactly to one of the n cells. So one of these generators would be like En of, whichever one, they're indexed. So there's 1 corresponding to each one. So this is one of my n cells that gets mapped onto my n minus 1 skeleton. The boundary of one of my n cells, where that n cell corresponds to the generator here, the boundary of that guy is just a copy of Sn minus 1. And you have an attaching map that tells you how to attach that Sn minus 1 to your n minus 1 skeleton. So that's your attaching map. Now once you have xn minus 1, what we can do is we can apply a quotient map where we collapse everything down to a single point except for a single n minus 1 cell. And it's like you can pick whichever n minus 1 cell you want. but it's going to end up with a single n-1 cell with everything else collapsed, and so the boundary of the n-1 cell gets collapsed as well, so you end up with a copy of Sn-1. And let's say this corresponds to index beta for whichever n-1 cell that was. What you have then is you have a map from this copy of n-1 of Sn-1, which was the boundary of your n cell here, down to another Sn-1, which corresponds to a collapsed an n-1 cell with its complement collapsed. So you have a map from Sn-1 to Sn-1. And if you just think about that map from Sn-1 to Sn-1, the composition of these maps, that map will have some degree. So this map is F. If you call this F, there will be some degree of F. And that's what our Dn is. Now, this might seem like a very weird abstract definition, but let me show you how it plays out in practice. In practice, let's think about this guy here. Your Z2 has two generators, an A and a B, that correspond to these two 1 cells that were mapped in with then their endpoints identified with X to give you two circles, A and B. We can think about where A and B get sent. So like this A, you can think this A corresponds to, you can think this A corresponds to like some copy of S1, right? You can think this B corresponds to some copy of S1 if you want. But I'm just thinking about like, what's going to go happen with this A and this B. So this A is a copy of S1. So it has some boundary. The boundary of A is just an X minus an X. So when you map where that boundary of A goes to, it just goes to X minus X. And so this A just gets mapped to X minus X, which is 0, which is telling you here that this A has degree 0. Oh, okay, I made a small mistake here. Dn, the way we define Dn is like this is correct, but you have to do it for every possible cell. So the proper definition here is Dn of an n cell, an n cell with the index alpha will come out to be just correspond to some n-1 cell with index beta, with in front of it some d of a alpha beta. This d of alpha beta is just your degree of f. Sorry. But then alpha, this n cell, you could collapse different quotient maps. You have different quotient maps to all the other n-1 cells. So that's why you have this index beta, because it's all the different n-1 cells. So you just send it to the sum of all the different n-1 cells. So this is indexed over the sum of all n-1 cells beta. Okay. But it's not going to matter here, because the same thing that happens to A, just like how A gets sent to 0, B also just gets sent to X minus X. And so that's 0 as well. And so your generators both go to 0, because you just look at this attaching map. It's just an attaching map here. You're looking at your attaching map, and it's just, okay, respecting orientation, it's just X minus X. So they both get sent to 0. And if both the generators get sent to 0, then the whole map is 0. Likewise, we can come over here, and we can ask, well, how about D2? Let's think about this 2 cell. So there was some 2 cell we attached here, some 2 cell we glued in, which we had thought of as the boundary. We attached it along the boundary of some two-dimensional guy here. So let's give that 2-cell a name. I'll just call it big C. I guess we can call it E2 for my 2-cell. Well, how did we attach this? What's the attaching map? The attaching map is literally you glue along A, and then along B, and then along A inverse, and then along B inverse. So if you think about where this guy gets sent, if you quotient, so you just end up with a copy of A. Then he will get sent to just gluing along A, and then gluing along A inverse. Well, that's trivial. So he'll get sent to 0 copies of A. But if you instead quotient along B, he would also, once you quotient out everything else, he would also get sent to glue along B, and then glue along B inverse. So it's 0 copies of B as well. So this is also the trivial map. So both are trivial. What that means now is your homology is straightforward. The cellular homology is just the kernel, which is everything, over the image, which is nothing. So for 0, it comes out to be of a torus, S1 cross S1. For 0, it comes out to be Z for n equals 0. For n equals 1, it just comes out to be Z squared, because it's the kernel, which shows everything, over the image, which is nothing. And for n equals 2, it's also just Z, because the kernel is nothing over everything. So for 0 and 2, it's Z. For n equals 1, it's Z squared. And it then is just 0, it's trivial otherwise. Okay, so that's how you calculate this stuff. So I almost think the example of a torus, like, it's too simple to actually have you understand this map. So like maybe this is a little bit mysterious still, because everything just gets sent to 0 when you attach it. So let me end with one more example that's very similar to the torus, but the attaching maps are slightly different, which will actually create something interesting in our homology theory. So let's end with one last example, which is the Klein bottle. So K is my Klein bottle. So give me the skeleton for a Klein bottle. You start out with a what? A single point. Yeah. Okay. So maybe maybe you just think about the classic representation of a Klein bottle like this, and this will help you. So it's like, how do you do a Klein bottle? Well, it's like a torus, but you put a twist on. So if maybe there's a twist on the A's, but you leave the B's untwisted. But notice this point is going to be identified with this point, which gets identified with this point, is identified with this point. So it's really just a single point. These are all the same point X. So you can think it was just a single point X that you added 2 1-cells to, and then you glue in a 2-cell. Where your attaching map here is going to be like A, B, A, B inverse. So the attaching map for your 2-cell is A, B inverse, following the orientation here. And what should I call my 2-cell? I'll just call it E2. Okay, so let's draw out the homology of this guy. So again, if I'm just thinking of my number of 0 cells, my number of 1 cells, and my number of 2 cells, this is simply going to be a copy of Z, because there's just 1 2-cell, 2 copies of Z for the 1 cells, because there's 2 1-cells, and a copy of Z for the 0 cell, and zeros at the ends. But now these maps, this map D2 and this map D1, get a little bit more interesting. Because let's think like how we attach these 1-cells. There were 2 1-cells here. Your 1-cells are A and B. But like how did we attach them? Well, I don't think this is too terribly interesting. Like how did you attach A to your point X? Well, it was just also both ends went to x, right? So you can think if you started off with just a single point x, the attaching map for A also just attached A like this. A was just attached with both endpoints, because both endpoints are on x. And B also is attached to both endpoints on x. So the one skeleton for the Klein bottle and the torus are the same. So these both, again, map to 0. These both map to 0, just like before. And so you end up with degree 0, and you end up with this map is 0. But where this gets interesting is the way you attach the two cell. So let's say this is my 2 cell E2. Okay, so I have like some 2-dimensional ball, E2, and I have an attaching map along the boundary of E2. So this is some map from the boundary of E2, which is S1, onto this one skeleton. How do you attach this onto here? Well, just read off the word, right? The attaching map is given by the instructions A, B inverse. So, when I collapse along A, where does this get sent to? How many copies of A? When I collapse along A, when I collapse, so A is the only thing that remains. I collapse the complement of A. So I collapse everything, so it's just a copy of A remaining. What do I end up with? I would have 2 copies of A. So this would get mapped to 2A. Whereas, where does this get mapped to when I collapse, so it's just B that remains? Okay, so I collapse everything that's not B. So B is now just a copy of S1, because everything else got collapsed down to a point. And what am I left with? Well, I glued along B, then I glued backwards along B. So I would end up with 0 copies of B. Remember, degree is equivalent up to homotopy. So attaching along B then backwards is the same as just going to 0, degree 0. Okay, so this is kind of helping you understand what's going on here, how these maps work. And then you can extend this map over any combination of A's and B's and so forth. But like, let's calculate the homology now. What is the cellular homology for 0 of the Klein bottle? H0 of the Klein bottle. Well, that's just your kernel over your image. That's just Z. Nothing interesting there, because your image here is 0. How about the cellular 1 homology of the Klein bottle? Well, that is this kernel, which is all of Z2, over this image. Now this is getting more interesting. It's the abelian group generated by A and B, because that's the kernel of this map. But the image of D2 is 2 copies of A. So you add the relation 2 times A is 1. So what group is this? The B, there's no relation on B, so B is just giving you a copy of Z. But the A has the identity that 2 times A is 1, so the A corresponds to a Z2 summoned. That's Z mod 2Z. And then when you calculate C2, the cellular homology, the kernel of this map. What's the kernel of this map? Well, the kernel of this map is just this copy of E2, because he gets sent to 0B.
You also get sent to 2A, which is not 0, so there is no kernel. Right. This kernel here is trivial, and the image is trivial, so the H2 is just 0. Very good. Okay. Making sure that was right. Yeah, E2 gets sent, is the only generator here, and he gets sent to, you can think E2 is being sent to like 2A plus 0B, if that helps. So this has no non-trivial kernel. So the kernel is just 0. So your second homology group is 0. Okay, and there you get the homology of the Klein bottle. I think you calculated the singular homology of this at some point, didn't you? Or the simplicial homology? Did some of you do this as a homework exercise? And you got the same thing, right? And so you had another way of seeing it. But this is showing you hopefully the power of cellular homology. So next time I'll either give a few more examples of this or I'll move on. But I encourage you, there's lots of spaces to calculate the cellular homology. Get used to these calculations. This definition seems quite abstract with degree, but really what it's saying is just keep track of how you're attaching maps or attaching things. That's what really this definition is saying. Just keep track of how you're attaching maps, gluing things, and then you can quickly calculate homology. So this becomes a very fast way to calculate the homology of a CW complex. We'll stop there.